All right, so we are today going to talk about extrasolar planets. And this field is a pretty young field because we only really knew about our planets and only our planets until the 1990s did we start discovering other planets. They had been theorized or hypothesized for quite some time, but until recently, there weren't any scientific experiments that could be done to discover these distant worlds. And so today I kind of want to focus on how we detect these other planets around other stars. How do we find them? And then next time we'll talk more about what those planets themselves, now that we've found all of these planets, what are they like? What are they, and what does it tell us about solar system formation? What does that tell us about the evolution of star systems and some of those sorts of things? But to understand why or how we detect them, we need to understand why is it so challenging to learn about them? And then how can the star's motion tell us that there's a planet around it, or how can the star's brightness tell us about the presence of a planet nearby? So this is one of the few direct images of a extrasolar planetary star system. And what you should notice is at the very center of the planetary system is where the star should be. But that star is missing in this picture. Stars are really, really bright. And the planets don't produce their own light. They reflect the light from their star. And so seeing the planets next to something so bright as a star is extremely difficult. These objects are extremely far away, they're extremely small, and so distinguishing between these small objects at great distance, or small appearing objects at great distances with huge brightness differences, is exceedingly tough. Right? Because the sun-like star is about 1 billion times brighter than the planets around it. But the planets are really close to the stars for the most part, relative to the distance that we're seeing them. Kind of an analogy that is used to describe the situation is thinking about being in San Francisco and trying to see a pinhead 15 meters from a grapefruit in Washington, D.C. Right? This is the level of sophistication of telescope that's required to detect other planets. And so in order to detect these planets, we have two kind of primary methods of planet detection. We have the direct methods, and we have the indirect methods. So the direct methods involve taking pictures or spectra of the planets themselves, whereas indirect methods involve measurements of the star that reveal properties about the orbiting planets. And most planet detection that is currently successful involves the indirect methods, two different indirect methods to be precise. As far as ways to detect these planets, the first one involves gravitational tugs. Large planets gravitationally pull on the stars that they orbit. And so a star should appear to wobble in position based on the planets orbiting around it. So for example, a distant star, a distant sun-like star with a Jupiter-sized planet orbiting around it would make that star move in a circle relative to us. All right, so this is the actual movement of stars. The stars themselves are wobbling because of the gravitational tugs from their planets. This one has not been very successful, this method. Just hasn't worked out too much. The amount of motion caused by these Jupiter-like planets going around the stars are very, very small. And so this has not been detectable for the most part. And things get pretty chaotic. Here are the orbits and suspected orbits of a star moving around some center of mass. So like the star itself is moving around the galaxy. The star is moving around a lot due to a lot of different possible sources of gravitational interactions. Taking all of it into account is pretty tough. And so that's why like gravitational tugs, this is a method I believe called astrometry, has only worked, I think, once so far. Yeah. As of now, one time this has worked that I'm aware of. The Doppler technique is an indirect method that kind of uses the same basic principle. But instead of looking at the light itself from the star and how that star appears to be moving, which we can't detect, instead we look at the wavelengths of light produced by the star. Because the star itself is made up of certain chemicals. It has certain, it has an absorption spectra or an emission spectra. And that means it has emission lines or absorption lines in its spectra. And when the star is moving towards us, that light gets blue shifted. So those absorption lines get shifted in the blue direction. And when the star is moving away from us, those absorption lines get pulled in the red direction. They're red shifted. And so instead of measuring the motion of the star, we're measuring the change in wavelength of the star's light. And then if these wavelengths, if there's this regular red shift, blue shift, red shift, blue shift, red shift, blue shift, and those shifts are of the exact same size every time, only planets can cause this effect. There's nothing else out there that can cause this sort of effect. And this technique, this Doppler technique, this has been called the radial velocity technique for finding extrasolar planets. And this was the first method that was developed that significantly worked. The very first extrasolar planet discovered was done so using this technique. And I believe just last year, the people that made that discovery got the Nobel Prize in Physics. So this is kind of a big deal recently. Altogether, something like 500 or so extrasolar planets have been detected purely by using this technique. So these are the each dot on this graph represents a discovered planet using this technique. On the y-axis, we have the mass of the planet. On the x-axis, we have the distance that planet is from its star. Most planets found using this method are Jupiter mass or bigger, and that the Jupiter mass stars have, or Jupiter mass planets have bigger effects on their star, and so they're more noticeable. It's a bias that's caused by the fact that the large planets are easier to find. And then most of these are also very close to their star. They're all, for the most part, less than 10 AU away from their star, so they're really close. This is essentially how they discovered the first extrasolar planet, 51 Pegasi b. What they saw was that the light was shifted by some amount every 4 days, and that it repeated the exact same pattern every 4 days. Here, the star's line, or the star's light, was getting redshifted up to 50 milliseconds in either direction, or meters per second, sorry, 50 meters per second in either direction. So it was getting 50 meters per second towards us and 50 meters per second away from us, and it was shifting between these two numbers every 4 days. And again, only a star with a planet can behave like this. So it's this regular shifting in the planet's light, and here they're measuring the shift: 50 towards us, 50 away from us, 50 towards us, 50 away from us, every 4 days. The shorter time period, or the shorter the time period is, the shorter the repeat time period is, the closer that planet is to its star. And then the bigger the shift, so if it's like, instead of 50, if it's 100, then it would indicate a bigger planet. So this first planet, that extrasolar planet, 51 Pegasi b, has a mass similar to Jupiter. It's basically the same as Jupiter's, but it is much, much closer to the star than Jupiter is. So Jupiter is at about 5 AU. This one is roughly 1/8 the distance of Mercury. It orbits every 4 days. That's a very, very fast orbit. And because it's so close to its star, it likely has a temperature above 1,000 degrees Kelvin, which has introduced the idea of this new type of planet called hot Jupiters. So hot Jupiters are kind of a new class of planet that we didn't really know about before. When we look at the graph for the radial velocity of stars, there are a few kind of shapes that pop out that tell us about the planets. So in the top two, we can see the difference between a small planet and a large planet. The amplitude of the waves are much bigger when you have a large planet. We can also determine how eccentric the orbit is. So if it's a very, very circular, it's like the bottom left, and it's very oval orbit, it would be like the bottom right. So these Doppler shifts, these radial velocity measurements, in addition to helping us tell or detect the planet in the first place, it can also help tell us about the mass and the shape of the orbit and the distance that the planet is from its star. And then there's even multi-planet systems, so where there's multiple planets in the same star system, and all of their effects involve each other. They all influence one another. And so for these sorts of situations, it can get very, very complex. But we have some very advanced math that does allow us to pull these these factors out. One problem with this detection method is that we only get the minimum mass of the planet. We can't get the exact mass. And the reason is that we don't know the inclination of the planet around the star. So what we're measuring is the effect as if it were straight on with us. What I mean straight on is that the planet orbit plane goes through the star's equator, so that everything is in a perfect line. The star or the planet is going directly orbiting at the equator, and that both of those are in the same plane as us, and so us as an observer. So we are seeing, not only is the planet orbiting perfectly around the star, but we are seeing it from that perfect vantage point as well. This is most likely not the case all of the time. And so what we're measuring due to this assumption is the minimum mass. The planet could actually technically weigh more. It could have more mass if it was inclined. So if it was out of the plane. But we can't see that. And so we can calculate the minimum, we can't calculate the maximum. We know it's at least so big. Another mechanism to find planets relies on that same sort of geometry. And this method is called the transit method. The idea is that the planet orbiting the star far away will, if it's oriented correctly, block the light from the star as the planet passes in front of the star relative to us, the observer. Now again, for a lot of planets and for a lot of stars, this is likely not possible. But when you look at enough stars, you can find examples where this does happen. When the planet passes in front of the star relative to us, it blocks the star's light just a little bit. But if that blocked light happens at a regular interval, only planets can explain that phenomena. There's nothing else that can explain the regular dimming of a star by the same specific amount over and over and over and over again. So this is what is known as the transit method. We measure very accurately that dip in brightness. And then from that, we can tell the radius or the volume of that planet. So we can't get the mass, we can only get the radius. Because we're saying how much light is blocked, and that depends on the size, not the weight. But also, depending on how long this periodic effect occurs, that tells us how far away the object is from the star itself as well. So is it on a 4-day orbit or a 10-day orbit? That tells us how far away the object is from the star. So this is kind of the same sort of thing. A transit passes the object in front of the star, resulting in a dip in brightness. And actually, in some cases, when the planet passes behind the star, some of the light gets enhanced. You see extra light because the light of the star is reflected off the planet and back to us as well. Let's see, what else? Questions so far about transits or radial velocity? Right, so The majority of discovered planets using this at all use this technique. The majority by far of discovered planets were found using the transit method. It turns out this is a highly effective method when you look at large numbers of stars. And I'll talk about one specific mission that did the bulk of the work in just a moment. Here, each dot represents a planet, and the lines represent the amount of error potential. So they're saying that it might be from this big to this big, and from this distance to this distance. So they're showing the error bars. There's definitely a planet there, but it might be bigger, it might be a little smaller, it might be a little closer, it might be a little further. So the error bars are included here. Some of these planets that transit their star even allow us to see their atmospheres. So in this picture here is a transit of Venus, but you can see Venus's atmosphere in the bottom right lit up by the sun. And if we measure just this light that's passing through the atmosphere, we can actually get spectra of the atmospheres of exoplanets. And this is really important because one major biomarker can be found by looking at the spectra of exoplanetary atmospheres. And it hasn't been seen yet. But if there is free oxygen in the atmosphere, if there's oxygen in its molecular form in the atmosphere, this, as far as we know, would require there to be life on that planet, and that only photosynthesis occurring over billions of years is capable of providing oxygen in large quantities in its molecular form in the atmosphere. And so this is something that's really exciting in the extrasolar planetary studies right now, is looking at the atmospheres of these different transiting planets. And again, nothing has been found in regards to that oxygen signal, but that is a big thing that people are looking for, particularly in the Earth-sized transiting exoplanets. So one kind of thing about the this actually diagram shows why the inclination matters. A planet that is inclined perpendicular relative to us as the observer cannot be seen using the transit method. So HAT 7 in this example could not be seen by an observer here on Earth, because the planet has to pass in front of the star in order for us to see that dimming of light. So the HAT 7 star, we would never be able to see that planet. It has to be more like the case below, like Gliese 1214, where the orbit is roughly in line with us as the observer of the star and of the planet. We have to have that planet cross directly in front of the star relative to us. And because the star is a large object, we get a couple degrees of wiggle room, but not much. There's not much to go on. Once you get too inclined and you're out of the plane and you don't pass in front of the star, we can't see it. What else? So one Jupiter radius is about 1/10 of the sun's radius and blocks out about 1% of the parent star's light. So our detection methods need to be able to measure 1% changes in light to find Jupiter-like planets, whereas Earth-like planets, one Earth radius is about 1/100th the sun's radius. It blocks out about 0.01% of the star's light. This means that in order to see a Earth-like planet, our technology needs to be 100 times more accurate than what would be required to see the Jupiter-like planet. We need to see the differences at the 0.01% level and measure it very precisely, 1 part in 10,000 accuracy. This is a high degree of precision, and this is the main reason that took it so long to detect other planetary systems. And that precision of this caliber just didn't exist really until the 1990s and 2000s. And then there's Kepler. So Kepler is the big mission that did the bulk of the work in finding extrasolar planets. NASA's Kepler mission was launched in 2008 and was set just to use the transit method. The whole thing was designed. We are going to look for stars that have planets crossing in front of them. It can measure a 0.008% decline in the brightness when an Earth mass planet passes in front, it transits a sun-like star. So notice that the Earth-like planet detection limit was 0.01. This can go to 0.008, so it's better than the required precision, but not by a lot. And it has found over 4,000 planet candidates since 2015. So the number of known extrasolar planets has increased dramatically since the Kepler mission. Let's see if I can get this movie to work. Okay, 1 second here.
We have an innate curiosity about our origins. Is life in our galaxy common? Does it exist? Are we alone? How unique is life here on Earth? The Kepler mission is one step in answering that question.
Kepler mission is a huge step forward in answering the question, what is our place in the universe?
The Kepler mission is NASA's first mission capable of finding Earth-like planets orbiting other stars in the galaxy in a region around the star we call the habitable zone.
The habitable zone is where we think water will be. If you can find liquid water on the surface, we think we may very well find life there. So that zone is not too close to the star because it's too hot and the water boils, not too far away where the water is condensed and ice covered, planet covered with glaciers. It's the Goldilocks zone. Not too hot, not too cold, just right for life.
The primary science goal of Kepler is to answer the question if Earth-like planets in our galaxy are common or rare. Kepler is going to detect planets via the transit method. What we aim to do is to measure the brightnesses of stars very, very accurately for a very long period of time without blinking, so that when the planet passes in front of the star, the light output from the star is going to dim just a little bit. That star is going to blink for about 12 hours. and we will be able to measure that dip in brightness. And it's that dip that we call a transit.
Kepler is a different animal from the Hubble Space Telescope or the Spitzer Infrared Telescope because it doesn't take pictures. You won't see beautiful images that you see from Hubble because we're not doing that kind of science. Those types of missions like Hubble and Spitzer are designed to focus on specific targets.
If you hold your hand at arm's length with a grain of salt or a grain of sand, that's about how much of the sky you can see with a normal astronomical telescope at any one time.
Kepler has a field of view that's 10 degrees by 10 degrees.
Our field of view is about as big as your hand at arm's length covering the sky.
So rather than taking pictures of very concentrated parts of the sky, we're looking at taking a very broad snapshot of a lot of stars.
Kepler takes really fuzzy pictures, but the thing that Kepler is designed to do, and it does very well, is look for very small variations in the brightness of the stars.
An Earth-like planet passing in front of a sun-like star is going to cause the brightness of that star to dim by only 1 part per 10,000. That's like looking at a headlight from a great distance and trying to sense the brightness change when a flea crawls across the surface. But the Kepler instrument is designed to detect such small changes in brightness.
The Kepler sensors are CCDs. The CCD in your camera is about the size of one of your small fingernails. The CCD chips on Kepler are a couple of inches square in pairs, and there's 42 of those. In your camera, you might have a few megapixels. If you have a really nice camera, you might have 10 megapixels.
We have 96 million pixels, and they have very low noise, so we can find very small planets.
Once Kepler is launched from the Earth, it will go into what's called an Earth trailing orbit. Astronomers call that a heliocentric orbit, which means sun-centered orbit.
It looks at the stars continuously, day and night, 365 days a year, and it slowly moves away from the Earth, orbiting the sun by itself.
And from there, it will point itself at the Kepler field and stare at the Kepler field nearly without blinking for 3.5 years at least, maybe longer if we have an extended mission.
Kepler will be looking in a region of the sky that you'll see almost every night in the summertime.
The field of view is kind of nestled underneath the wing of Cygnus, the swan, between Cygnus and Lyra. Now, in that area of sky, there are something like 6.5 million stars. Why do we need so many?
Because of the way Kepler looks for planets, we have to have planetary systems that are lined up so that the planet actually passes between the star and Kepler telescope in its orbit.
The probability of that happening if you just throw stars randomly down in our galaxy is something like 1 to 10%. It's small. So of those 6.5 million scattered over that 100 square degrees, only maybe 200,000 are interesting to us.
We select the 170,000 or so that are most suitable to look at for planets with the Kepler telescope. Finally, we expect to end up with somewhere between a few hundred and a few thousand signals that are really planets around the stars that we're looking at.
Well, this is the first time that photometry, the measurement of the brightness of stars, will ever be done at this level of precision. And it will be done simultaneously on more than 100,000 stars continuously over a period of years.
We're somewhat like pioneers, very much like the explorers that were looking for new lands to settle. And that's how I see what we're doing. We're looking in this region of our galaxy for other habitable worlds.
I think people everywhere want to know whether with all the stars out there, do they have planets that are Earth-sized? Are Earth frequent or are they rare? And this gives us that answer. It's the next step in mankind's exploration of the galaxy.
There's two extreme answers that Kepler might give us. It might tell us that there's an Earth-like planet practically around every star we look at. Imagine the possibilities for life in the galaxy or life in the universe.
If, on the other hand, we found out that Earth was very special and that the typical star, like the sun, is not hosting planets like the Earth, I think that would be a real surprise as well and would really make us reconsider the special nature of Earth.
We are now finally at the point where our technology allows us to build a machine that can make the observations to scientifically answer this question.
How many stars like the sun did develop planets around them like the Earth? I think that's such an important question to everyone and so interesting that we really have to do it, and it's a once-in-a-lifetime opportunity right now.
All right, so that's an intro to Kepler. So if we look at, again, kind of all of the planets that have been found by transits, it looks like this. And then Kepler is responsible for all of these. All right, so you can see that Kepler did basically all the work. There were other ones, but Kepler was super critical in determining the locations and nature of the wide majority of transiting exoplanets. We saw Kepler's camera. It is 96 megapixels. And it points in the exact same location of the sky while collecting data. And it focuses on that particular location all year round, and it did so for several years before the mission ended. Here you can kind of see the search space for Kepler. It was kind of a cone shape passing through the Sagittarius arm of the Milky Way galaxy, looking back about 3,000 light years. If you were to look in the sky that far away from Los Angeles with all of our light pollution, this is the location in the sky. And it's about the size that if you were to hold your fist into the air and look, that's about how much of the sky would be looked at by the Kepler telescope. The idea for this telescope came around in the mid-1980s, but it just didn't have the technological abilities until significantly later. And the goal was that we knew not every star would have detectable planets. Some of them would have planets that could not be detected. But if we looked at a large enough sample of stars, we would be able to determine the fraction of sun-like stars that would likely have Earth-sized planets in Earth-sized orbits. And so that's why they looked at, they had, I think, 6 million stars to pick from. And they picked out about the best 200,000 of those 6 million and focused on those. In the middle of the mission, Kepler kind of broke. One of the gyroscopes that control how Kepler moves broke. And so there was actually a very kind of critical discovery using the remaining gyroscopes and the solar wind to both combine to control the direction that the spacecraft looked. And so they were able to extend the mission using this kind of complicated geometry and broken spacecraft technically. But they were able to extend the mission for quite some time, and that allowed for the discovery of many more planets as well. So Kepler takes data that looks like this. It focuses on particular planets or particular stars and measures their light very, very, very accurately. And then occasionally it comes out that there is a dip in the amount of light produced by that star. And if that dip happens on regular intervals, only planets can cause that. So Kepler, it produces data like what we're seeing here. It's optimized for finding Earth-like planets in Earth-like locations around sun-like stars. And it successfully measured about 5 years worth of data. One thing that's kind of critical to think about in particular as we start to think about these planets more next time is that the habitable zone for a star depends on the temperature of that star. So the smaller stars are colder, and so their habitable zones are closer in. And the bigger stars are hotter, so their habitable zone is further away. Habitable zone is defined as the location in a solar system where liquid water would be stable at the surface of a planet. So kind of a technical definition for the habitable zone. And so the habitable zone location depends on the temperature of the star, which depends on the mass of the star. So an Earth-like location is not always going to be habitable. It might be too hot for a big star, it might be too cold for a small star. But we want to look at all of these different distances to look for all of these types of planetary environments. And actually, this is something that you can do if you want. There is a citizen science effort to look at Kepler data. And I think there was a high school student that actually just discovered, I think, 2 new planets using Kepler data just within the past year. So it's definitely still possible to find these planets. There is a new spacecraft that launched about a year and a half, maybe 2 years ago, called TESS, where you can do the same thing. It's a brand new telescope. It's been operating for a little while now. It needs more time, but it uses the same method that Kepler does. It looks for transits, and I think there's a citizen science effort behind TESS as well. So if you are interested in trying to find these extrasolar planets on your own, let me know, and I can connect you to these citizen science efforts. Maybe you could discover a planet. And just like before, when we have planets extrasolar planetary systems with multiple planets, those light curves can get pretty complicated because those planets, their effects add up. So you might be blocking 3 times the light when you have 3 planets in front of the star, and their orbits get all chaotic. It's pretty messy, but we do have the math to try and find these sorts of situations. So in 2009, before Kepler, here is the graph showing the known transiting planets, right? Not a whole lot. With Kepler by 2010, we've essentially tripled the number, and by 2011 and 2013, it's gone crazy, right? We have, I think, almost 5,000 or 4,500 Kepler planet candidates altogether now, in a wide range of sizes. Notice how many Earth-sized planets were discovered. Something like 100 Earth-sized planets were discovered, or smaller. Thousands of Jupiter and Neptune class planets. And then based on the statistics, it is now expected that nearly every sun-like star has planets. It's expected that almost every sun-like star has a planet. has at least one planet. There's a 15% chance that that planet would be an Earth-like planet, a 15% chance that that planet would be a super Earth-like planet, and about a 30% chance, or a 20% chance at least, that that planet would be a Neptune-like planet. So almost all stars have planets, and usually they're going to be towards the smaller end in size. So this is good news. From that video we were seeing before, there were kind of the two end members. One where there's lots of planets around stars, which this is what it seems like the case is, instead of the other case where there's not a lot of planets and that Earth is very special and Earth is alone. It seems that there's a lot of Earth-like planets out there. There's a lot of potential for these terrestrial planets to form around other stars. Forming Earth-like planets seems like a normal thing for stars rather than a special thing. It's just now, do those Earth-like planets also form life? That's the big question next. If we look at the stars around the sun is a G star. So there's 20 other G stars, 44 K stars, 246 M stars. Those K and M stars are cooler, smaller stars, which are more common. And then there's only 10 stars that are bigger than the sun, really significantly. 6 F stars and 4 A stars. It seems that the smaller stars are even more likely to form planets than the big stars. So let's see. And then these are looking at stars with periods less than 50 days. This is an important number because 50 days tells us about the orbit size. And so the longer the orbit is, the more data we need to confirm the planet's presence. And so finding these short orbits is kind of important because we are limited on time and how long we can collect data for. What this means is that to find the habitable zone planets, we need to focus on the colder stars because we can't look for long enough to find the planets in the habitable zones of the brighter stars. So we kind of focus on these colder, dimmer stars, the M stars, the G stars, the K stars, not the A stars, not the F stars, not the O stars. Right? The big stars, we can't look at their habitable zones easily because we just don't have the amount of time required to collect the data. So we focus on those colder stars, and it looks like, based on studying those colder stars, that your average M star will have 1.5 planets, right? So that means it's more likely to have 2 planets than it is to have, or it's just as likely to have 2 planets as it is to have 1 planet. There's lots of planets. Your average star has a planet, is what this is telling us. Now, those were both indirect methods of planet detection. The transit method and the radial velocity method, they do not directly find the planet. They look at the star and infer the presence of the planet based on what's happening to the star. Direct detection is possible. It is exceedingly difficult. The main thing that has to be done is that you have to block out the light from the sun itself and filter all of that light out. This has been successful in a couple of cases. So here we're seeing one of those cases of a direct detection where a object moved locations around this star that we can't see, it's been blocked out, but in this dust disk around that star, the planet changed location from 2004 to 2006, and there's that zoom in kind of showing that. Direct detection, there's only a few of them. They're plotted here. These planets are in general pretty big. They're also significantly further away from their star in most cases as well. Most of those direct detection planets, right, there's just a few dots on this slide here, are from this one particular system. So 4 of the planets that were found via direct detection are in the same planetary system. That's HR 8799. And so C, D, E, and B, I think, are all present here. They're named in the order in which they were discovered. So B, even though it's further away, was discovered first. So B, C, E, and D, these are direct detections, direct imaging of these planets. And you can, again, see the star in the center has been mostly blocked out. They've used adaptive optics to block the light from that star. We saw this case, this is for Fomalhaut B, which actually I've heard just this month, there's some question whether this is a planet now. So that it was added to the inventory of extrasolar planets quite some time ago. As of this month, it was removed. So this one I'm kind of curious about what's going to happen. Beta Pictoris B is another example. Direct detection. And again, it mainly requires this very, very powerful adaptive optics technique. We've got to block out the light from the star. It's tough. It's tough, but we can. It is a successful method. There are 2 other methods as well, one more successful than the other. It's assumed that we can look at features in dust disks to predict the locations of planets that are in the formation process. Although we would not be able to see the planet itself, we could infer that one was there. There's also a process known as gravitational lensing, which literally requires stars to align in order to detect planets. So this one cannot be done on purpose. This is just a pure accident of nature. But when it happens, it allows us to detect the presence of a star or of a planet around a star. The way it works is due to relativity and Einsteinian gravity. So the idea is that large objects bend space and time. And since they bend the direction and path that light travels, because they bend space and time, you get a lensing effect. So you get an enhancement in the amount of light that reaches us, the observer. And so, again, this requires stars to align. So the idea is that there's some background star, and if you measured the light of just that background star, you would get a strange light curve if there was a star in the foreground that had a planet. Because as that planet and lensing star get in the way, they bend the light from that faraway star. And so now that star's light can take multiple paths, and it enhances the amount of light that was seen. And so it makes a light curve kind of like what you see above, where you get these 2 super enhanced blips of brightening of that background star. And this can only happen if the foreground star has a planet. So it's a lot of fancy math, but essentially you get this lensing effect. It magnifies the brightness of the star. Here's kind of another view of it where, especially in the picture on the right, you can see that the star is getting brighter and brighter and brighter because of this close-up planet or close-up star, this stellar lens. But then it gets even this extra blip because of the planet that's present. If the planet is orbiting, it gets the extra blip. And something like 10-ish stars or so have been found using this gravitational lensing method. Again, this is a pure accident of just space. Stars literally have to align for this to happen. You can't force this observation to occur. It either happens or it doesn't. And it has happened a couple times. There's a lot of stars out there, but this is not a technique that you can rely on. We can't build a device to make this happen and observe it on purpose. It just is kind of an accident. And there's features in dust disks. We kind of talked about this as evidence for us understanding solar system formation processes earlier in the semester, but that is one additional way. So yeah, these are good evidence, but it's kind of hard to make these observations consistently. Then as of today, there are 3,262 confirmed exoplanets. Confirmed meaning that they've been detected in 2 different methods at least. They've 2 separate detections of these planets in order to become confirmed. There are 2,485 unconfirmed exoplanets. So these are considered exoplanet candidates. They've been detected by one method, but haven't had that subsequent dual detection. Altogether, that is 5,747 extrasolar planets. Whereas in 1990, we knew about only the planets in our solar system. So we've gone from knowing our 8 planets plus Pluto to over 5,700 planets. Here is kind of the rate of publication, right? So around 1990, we get our first planetary discoveries, and then it just ramps up when Kepler gets around. Here's all of the extrasolar planets that have been detected to date. The brown dots in the upper right, that's HR 8799. These are all the brown dots represent the direct detections. The blue dots are the radial velocity detections. The red dots are the transit detections. And you can kind of see some green in the middle right area. All the green dots represent the gravitational lensing. And then this graph is showing again kind of the separation of the planet. So that's going to tell us whether it's in the habitable zone or not, depending on what star it is. It's also telling us the planet mass compared to Jupiter. So Earth is about 1% of around that 0.01 line compared to Jupiter. And so we found a lot of planets that are smaller than Earth, a lot of Earth-sized planets as well, a lot of super Earth planets. These are all interesting targets to continue looking at and exploring further. Here we have, again, kind of the discovery year of extrasolar planets. You'll see that basically the red radial velocity and the green transits, that's the reliable methods for finding extrasolar planets. The radial velocity came first, but it's still doing a good job. Transiting came later and caught up very quickly and then surpassed radial velocity. as far as finding the planets. But most of those detections were in 2 primary years. Kepler did its primary work really quickly and really early on, and then we don't really have anything else. TESS is the new satellite that's working on making new transit detections, but basically we've just got to wait on the spacecraft in order to continue making these detections and continue finding extrasolar planets in the future. Without future missions, we just won't be making these same sorts of detections anymore. So to recap, let's watch one more movie and then we'll call it a day. Let me switch the screen.
As of last year, from a statistical standpoint, we now know that there are 1 to 3 Earth-sized planets or smaller around each and every star in the galaxy. The next time you go outside and look up at the night sky, just pick a random star. Planet.
2 of them.
Probably 5.
Yeah.
5 planets, one of them sitting in the habitable zone.
Okay, well, so this is just a table of the 5 sort of most prominent exoplanet detection techniques.
The way we discovered the first planet outside of our solar system was using a technique that we call the Doppler technique, or radial velocities.
They measured the velocity of the star as a function of time. And here's 0, and there are plenty of stars that just look like this. They're moving away from us, but at a constant rate. So there's probably nothing there. But if you see a star with a velocity, it's changing and it maps out a nice sine curve.
And then you ask the question, well, what do you know about physics that could possibly be making it move? Well, something must be tugging it.
It's the same way that you can tell how fast a car is moving or a train by its sound.
The faster the star is moving towards you, the closer together the wavefronts would be, and the higher frequency or the bluer the light would appear. And then the faster it's moving away from you, the redder it appears. You have your sun, and then orbiting around it is a planet. And when the planet is over here, because of gravity, the planet gets tugged inwards, but also it tugs the star ever so slightly inwards. And then when it orbits here, the star gets tugged over here, and same thing.
The period of this is 1 orbit, and the amplitude, how big it is, depends on the mass of the planet.
Which is why the first thing that we saw was...
They're called hot Jupiters.
Because astronomers are very clever with their naming.
Right.
What we're actually observing is the spectrum of the star.
But seeing the whole curve is really hard to measure.
It'd be this featureless thing with nothing to grab onto. All these lines give us a handle to measure the velocity of the star. Every single atomic and molecular transition happening in the star is moving, getting Doppler shifted in the exact same way. So every single line has a story to tell about the motion of the star.
And right now we can do like 1 meter per second, which is walking speed, which is really slow. It's 100 light years away. The shifts that we're talking about for these planets are extremely small.
We're sampling this with a little CCD detector like the one in your camera phone. So we're watching the line shift by about 100th of a pixel, which is about the same size of 80 silicon atoms lined up end to end.
That's crazy. Yes. We are living in the future.
So the analogy there is that you're standing right next to the world's brightest lighthouse and you flick a lighter on. The act of seeing planets is analogous to being able to discern that flame next to this lighthouse when this lighthouse is in California and you're standing in Hawaii. That's the scale of the problem.
And the only reason why we can even do it now, today, is because you have these crazy adaptive optics technique. And this allows you to take away the blur of the atmosphere. And with that, we've been able to see exactly 4 other planets.
HR 8799b, C, D, and E.
And then there's like light curves that are searching for planets that transit. What we do is, again, we point our telescope at a whole bunch of stars and we just track how much light we can see from them. And if we're staring directly face on and you have a planet and it goes in front of the star, the light from the star goes down, so you just see a constant dip. And then it leaves the star and slowly goes back up. You try to find dips, periodic dips in light.
You have a big planet and a small star, look how deep that goes. There's a tiny planet, that little dot right there, causing this tiny little dip in light. and you have kind of intermediate to both cases.
You have to be so precise you can see 1,000 difference.
So Kepler was launched 3.5 years ago.
And every 30 minutes, it takes a measurement of the brightnesses of 160,000 stars.
So you have to look at a lot of them because just geometrically, the planet has to pass between you and the star. So Kepler has found about 2,500 what they call candidate planets. So we talked about transits here, and we have a star with a planet going around it. The planet has a very irregular orbit. So now let's say we have a second planet in here.
So the outer planet can tug on the inner planet and cause it to arrive late to its transit. And then a little bit later, it's ahead of it and it pulls it forward and it causes it to arrive early for its transit.
So you actually see a nonlinear period.
Then you can say beyond any reasonable doubt.
You have two planets here.
If you want to really get down to magic, then you really have to get into relativity. Let's say we're standing over here and we're looking at a star here, far away from us, all right? And then let's say that there's light from another star way back over here. The photons that travel from this star, when they get into the gravitational field of this star, it actually gets bent by the gravity of that star, because anything with mass bends space and time, and it actually acts as a lens, so it's called microlensing. So people were doing that for a while, and then one day they got a secondary blip, and that's because this guy brought a buddy with it. He had a planet, and this lensed light got lensed again.
Double lens.
When the planet was drifting by as well. One of my colleagues who does the Doppler technique, so she raises her hand in the middle of the talk. She's like, let me get this straight. You are measuring planets that you never see around stars that you never see. Is that right? It's basically what you're doing.
So the thing is, in 20 years, the consciousness of humanity went from, gosh, I wish there's got to be like some planets out there, right? 20 years ago, right? To now, so there are literally billions, maybe trillions, of planets in our galaxy.
That's just our galaxy.
Yeah, the same number of stars that there are in our galaxy is the same number of galaxies in the universe.
Roughly, yes.
So there's a billion times a billion planets,
Yeah.
Conservatively speaking.
And once
You're
you
right.
start seeing all these planets and how they're arranged, then that starts to give you insight into how they could have formed, how the whole system evolved over the
Right.
lifetime of that
In
system.
fact, now you're basically connecting those diffuse blobs of gas and dust out there
And how
to
they-
living beings.
That's what we're doing here. We're getting not only just finding planets, which is amazing in and of itself, but we're basically tracing our past as humans back through the cosmos, going from where we are right now back to those dust lanes. And we're doing so by looking for little blips in the light from stars. We're looking for little wobbles in the stars caused by the gravitational tug of a planet. We're doing it through general relativity. We're taking pictures of planets. All of that in and of itself would be cool. But it goes so far beyond that. But we're revising our own origin story.
So that is where we will stop today. Next time, right? So now we've discovered all of these planets, and what do all these planets, now that we know about, what does that tell us about solar system formation and the evolution of planetary systems in general? So that'll be our focus next time. Again, I want to remind you the midterm is on Wednesday and will be open for a week and will be the 3 questions that I showed. And also the project is going to be signed today. You should get your star today, maybe tomorrow morning. It'll definitely be there by tomorrow morning, your assigned star for the project. Any questions before we wrap up today's recording? And I'll also try and get that other recording for the other lecture back up soon as well. All right, that's it then. We will call it a day. I'm going to end the recording.